is investigating the electric potential near a charged sphere. The sphere is suspended from the ceiling as shown in Fig 2.1. A flame probe is used to measure the potential V at a distance L from the surface of the sphere. The experiment is repeated for different distances from the sphere. It is suggested that V and L are related by that equation, where theta Q is the charge on the sphere, A is the radius of the sphere, and that one is the permittivity of free space, epsilon naught. A graph is plotted of 1 over V on the y-axis and against L on the x-axis. Determine the expression for the gradient and the y-intercept. So here I did not write in advance so that we can see the procedure as we try to determine the expression for the gradient and for the y-intercept. The graph to be drawn is the graph of 1 over V on the y-axis and L on the x-axis. So we are going to have to make 1 over V the subject of the formula. So starting from what we have here, in this case we have this expression which I'm going to rewrite here. We have an expression saying, we have an expression saying V is equals to Q over 4 pi permittivity of free space L plus A. So that is the expression that we have. We want to make 1 over V subject of the formula. So the easiest one way here is to simply put V over 1, and on the other side we'll keep it as it is. Remember, we need to make 1 over V subject of the formula, and to ensure that L, since L is supposed to be on the x-axis, L is also separated, which I shall show shortly. So here, once I do this, I can invert both sides. Whatever I do to the left-hand side, I must also do to the right-hand side. So here it would then be, if I invert, it would then be 1 over V is equals to 4 pi permittivity of free space L plus A over Q. So one step is done. We have 1 over V on the y-axis made the subject of the formula. So the next step now is to have L. L must not be added to something. It's better to have L being surrounded by things that are dividing L and things that are multiplying L. That way it can be separated into the form y is equal to mx plus c. As you can see, x is being multiplied to m before it is added to c. So we want to have a similar situation whereby we have L being multiplied to something before it is being added to something. As it stands right now, since L is in the bracket here, the first thing that is happening to L is the addition of A, so which is what we want to reverse. So the best case scenario to do that one here is to simply expand the bracket. In this case, we'll say 4 pi permittivity of free space L plus 4 pi permittivity of free space A over Q. So once it is like that, it is now simpler. We rewrite 1 over V here is equals to 4 pi permittivity of free space L over Q. Then next we say 4 pi permittivity A over Q. So as you can see, we have managed to achieve what we wanted to achieve. So if this is going to be on the y-axis and L is going to be on the x-axis, then I can write this equation of a straight line corresponding to everything. So here I would say M corresponds to this, X corresponds to L, C corresponds to all of this, and Y corresponds to 1 over V. So since M on the equation of a straight line is a gradient, then we have found the expression for the gradient and the expression for the y-intercept. So we can now successfully write those expressions those expressions in the space provided. So we can now say gradient equals to 4 pi permittivity of free space L, sorry, no L there, over Q. Then we can also say 4 pi permittivity of free space over Q. So we found the expression for the gradient and for the y-intercept. Now it might seem like it is just a simple mark of 1 mark. So what about all this work for 1 mark? No, but it's not about 1 mark. It's about what will follow once we have drawn our graphs and the likes. We will use this data a lot. We will utilize this information a lot. So let's go to the next step now. In the next step, we are given by the question, values of L and V are given in Fig 2.2. So as you can see, this is what we have in Fig 2.2. Then the question asks, calculate and record values of 1 over V, stroke 10 to the power of minus 3. So in other words, we are going to have to remove 10 to the power of minus 3 from what we would have found. Now, we are looking for 1 over V. As you can see, the first value of V is 1.25 times 10 to the power of 3 because it is in kilo. It is in kilo, as you can see here, it is in kilovolts. So it's times 10 to the power of 3. So when you divide 1 divided by 1.25 times 10 to the power of 3, mathematically you can understand that the 10 to the power of 3 can simply rise to the top to become 10 to the power of minus 3. So in which case we are only worried about dividing 1 and 1.25. Then this becomes 0.8. So in other words, we are getting 0.8 times 10 to the power of minus 3. 0.8 times 10 to the power of minus 3. So we have to be very careful there. 0.8 times 10 to the power of minus 3. So we don't need to write the 10 to the power of minus 3. As you can see on this column heading here, 10 to the power of minus 3 has already been put on top there. Just like in the first column heading, kilo was already on top there. So it was 1.25 times 10 to the power of 3, but the kilo was already on top there, so it was just being written 1.25. So here we can just write 0.8. But however, we must be very adherent to significant figures. Why? Because as you can see, we have used 1.25, which is to 3 significant figures. So if 1.25 is to 3 significant figures, then our answer that we get must be to 3 significant figures or plus 1 more significant figure. So our answer has to be 0.800. These zeros after the 8 being significant. So this is 3 significant figures without fail. So we continue with the rest. 1 divided by 1.05, which gives us 0.952. And remember, we need it to be 3 significant figures. So 0.952, again, 1 divided by 0.9. This becomes 1.11111. But since 0.90 is to 1 significant figure, we can just leave our answer as 1.1. It is the 2 significant figures, this one. So our answer can be left to 2 significant figures. Okay, 1 divided by 0.8. Again, that gives us 1.25. Since 1.25 is to 3, we can leave it to 3 because since 0.80 is to 2 significant figures, we are allowed to leave our answer to calculate the value to 2 or plus 1. But I want to be consistent here. If we have used for 1.25, which was to 3, we used 3 significant figures for the answer. For 0.90, we used, which was to 2 significant figures. Our answer calculated, we used 2 significant figures. So let's just be consistent throughout. So here I'll write 1.3. Then I'll do the same. 1 divided by 0.7, which gives me 1.428, something like that. So ultimately, if I were to round that one up to 2 significant figures, that's 1.4. Then the next one is 1 divided by 0.6, which gives me 1.6666666 to two significant figures. That's 1.7. So I have finished the first part of the column. Now, they also say include the absolute uncertainties in 1 over v. Now, that's where it gets tricky now. To find the absolute uncertainty in 1 over v, it's not an easy thing. Neither is it a very tough thing. We are given the uncertainties of v, but we need to find the uncertainties of 1 over v. So we have to use uncertainty rules. And which rule do we use? Here, I'll use the rule which says a is equals to x over y. If you are to find the uncertainty here, there's no way you can find delta a, which is the uncertainty of x over y, because there's division in this case. There's no way you can find delta a directly before you find the fractional uncertainty. So first things first, you must find the fractional uncertainty, which would be delta a over a is equals to delta x over x plus delta y over y. Then after this one now, you can now say delta a is equals to, in brackets, delta x over x plus delta y over y multiplied by a. You're multiplying both sides by a, so that, but you know already what is a in this case. So delta a over a is equal to delta x over x plus delta y over y multiplied by a is x over y. So in which case, that's how we find our uncertainties. So now, having established this, I'm now going to erase this so that now I can do for the real thing. This is how we do when we are dealing with a division. In this case, we have division of 1 over v. We have uncertainty of v, so we want to find the uncertainty of v. So I'll say again, a in this case is equals to 1 over v. I want to find delta a, that's the uncertainty of 1 over v. But to do that, I must first find the fractional uncertainty. To find delta a over a, the fractional uncertainty of the numerator 1 in this case is 0. A constant does not have a fractional uncertainty. Neither does it have an uncertainty in this case. So I'm only left with the denominator, which is delta v over v. And the next thing, I then say delta a is equals to delta v over v multiplied by a. But I know the value of a, as I have said on top there. Delta v over v then becomes multiplied by a, which I have said to be 1 over v. And to simplify things, I'll just say delta v over v squared. So when we do this, we have simplified things. Delta v over v squared. Now, there's not going to be much problem as regards with the 10 to the power of minus 3. We're just going to ignore it as if it is not there. Of course, you have to be careful when you're dealing with the different papers. So in this case, every time I'm going to, for example, firstly, I'm going to take, as an example, I'm going to say 0.05, which is the uncertainty of 1.25 there, divided by 1.25 squared. That's how I find the first uncertainty. So what do? I say 0.05 divided by 1.25 squared. That gives me, 0.05 divided by 1.25 squared. That gives me 0.032. Now my uncertainties, I must always, if it can help, I must always try to keep them to one significant figure. In this case, I'll then write plus or minus 0.03. Then the same thing is done again. It's now 0.05 divided by 1.05 squared, which gives us 0.045. One significant figure is 0.05, like that. Then the next one is 0.03 divided by 0.9 squared. This gives me 0.1 0.04. Okay, then the next one, it's 0.03 divided by 0.8 squared. That gives me 0.05. Then the next one is 0.02 divided by 0.7.